Rate limiting is hard. There are some quick solutions, but as a problem overall, this is a complex topic, and I'm really excited that a community member actually wrote an article about it. I've been wanting to read this one for a while. Pumped we're finally getting the time to do it. Let's take a look at visualizing algorithms for rate limiting. Why rate limit? Imagine a Twitch chat with many active participants and just one spammer. Who could ever imagine that? Definitely not an experience I've had before. Without rate limiting, the sole spammer can easily dominate the entire conversation. With rate limiting, however, each user has a fair chance to participate. Yep. So right now, the spammer is sending tons of requests, and every other user has some going in, but you can barely even see them in chat. A rate limiter lets you control the rate of traffic that your service is processing by blocking requests that exceed a set limit during a period of time. So think of that like you have every 10 seconds you can send one message. There's actually a setting for that on Twitch where I can do chat settings, slow mode, which is effectively rate limiting built into Twitch so that when I check one of these options, then you can only send a message every 30 seconds or 5 seconds or however often I choose, which helps keep it so that individuals can't spam chat quite as hard. They even have some good examples here. It's useful beyond just throttling spam and chat. Like if you have something like a login form, you don't want people to be able to brute force and just spam until a password gets guessed correctly. So every time they try to get in, you limit how often they can do it. I was actually trying to get into a site yesterday. When I signed in, I typed things correctly, but it auto hit enter for me effectively when I used one password. And then I hit the login button. So it sent 2 requests instead of 1. And I got rate limited and I wasn't allowed to get into my account for another 2 minutes. But that's terrible as a user experience, but also important because it means people can't just spam passwords over and over to try and break into your account. API endpoints are also frequently rate limited to prevent any single user from monopolizing resources. Imagine that you want users to only be able to hit an expensive endpoint 100 times per minute. You can track the hits with a counter that resets every minute. Any request after the 100th within the minute would get blocked. This is one of the simplest rate limiting algorithms, called the fixed window limiter, and it's a common way to control traffic to a service. Yep. Very, very common. I use this in a lot of the things that I've demoed and the products that I've showcased in my tutorials and my previous videos. Using something like Upstash in their rate limiting SDK lets you set this up with like 3 lines of code. And that's enough for a lot of things, but not for everything. And I'm excited to see how this article breaks it down. As they say, it's not always that simple. When does each 1-minute window begin and end? If I begin a burst of requests near the end of a window, can I exceed the limit? Is the window's capacity restored one request at a time, or is it restored all at once? In this post, we'll explore the 3 most common algorithms to answer each of these questions. I actually don't know the immediate answer for this, which is interesting. The 3 options are fixed window, sliding window, and token buckets. Let's figure these out. Here's the fixed window example. A set number of requests can be made within a predefined time window. Requests increment a counter that's reset to 0 at the start of each window. So notice that this time window starts regardless of when you send something, regardless of when a request happens. This window is an existing time frame that just exists via something like a cron job. So we know this happens within this window, and then messages happen to be sent. You even pause requests and see that the window stays exactly the same, even with no requests happening at all. I can also spam hit and see the result too. This is a really nice visualization. What are with all y'all insane devs and your crazy visualizations lately on these blog posts? So cool. So yeah, the pros are that this is simple to implement and understand, and it's predictable. Predictability is not necessarily a good thing, as I'm sure we'll get into. The con is that this allows for bursts up to 2x the limit. So yeah, if we're getting near the end here, then once we get close to the end, I could spam and then immediately start getting requests going through again. So you actually can do really bad damage in those short windows because you can up to 2x the damage in that frame. There's a real world example of GitHub's API, which uses a fixed window rate limit of 5,000 with a duration of 1 hour. And the start is set to the start of each wall clock hour. So every user is allowed to make about 5,000 requests per hour to the GitHub API. So if you make 5,000 at right before midnight and then 5,000 right after midnight, you're fine. But then the next request is what fails. So you can still send 10,000 requests to GitHub in a 2-minute window. You just have to do it at the right times, which is a real risk to consider when you're building things like this. Ooh, there's a tangent about 24-hour windows. Ooh boy. Apparently there's a subtle issue with the 24-hour limiter above. Its window resets every day at midnight, but midnight according to which time zone? A standard fixed window might reset its counter according to your server's midnight, or a standard time zone offset like UTC. A user in a different time zone who ran out of requests might retry just after midnight and be surprised if the limit hasn't been lifted, since to them, it's a new calendar day. For these applications, you need to offset your window starting according to the user's time zone, which has some potential for abuse as users can manually adjust their time zone once they've run out of requests to gain up to one full window of additional requests. Yeah, I don't recommend doing a 24-hour window, certainly not sharing that and telling people that the requests restart at midnight. Yeah, not like Twitch does that for certain features and things like the tracking of how often you stream. It's not like the best way to get partnered on Twitch fast is making sure you stream between 4 and 6 p.m. Pacific time, because that goes over the 5 p.m. window where they count it as 2 days instead of 1. Those totally aren't things. Interesting. Another way of doing fixed windows, which is how a lot of things will do it, is instead of fixing the start time on a set interval, each window can be created at the time of the user's first request within that window. So now, if I hit pause, nothing happens. Still nothing's happening. And the window that's 24 hours doesn't start until I do a hit. So now that I've done one, I can do up to however many this allows. I have one request left. And now I get errors until I do one after that first one's been 24 hours. So the window shifts based on not if it's midnight or not, but based on when your last, or in this case, first request was. But this sucks as well because now I can get more requests if I start at 23. So I'm starting now, and I was able to do more requests. But if I wait and I do nothing, so I'm just sitting here doing nothing, we're going past the window. Now I'm going to start spamming. I can only get half as many. So it's actually strategic to do a request every 24 hours so you can exhaust that existing window before starting the next one. As insane as that is, so is doing your rate limits in this way. But yeah, as the author says, it's especially important to show users the time remaining until the next window once they're limited, since there's no set time that aligns with those windows. Speaking of aligning windows, sliding windows. Instead of refreshing the capacity all at once, sliding windows refill one request at a time. So here we see there can only be 5 requests. The way it's showing this is vertically. So if I pause, right now we've done 2. I can do 3 more, and now we're going to have errors because there's no space in that vertical real estate. It's actually a really good way of visualizing how this works. And you can see they go gray once that requests limit has expired. So instead of thinking of this as like you have a buffer of how many requests you could do, each request has an amount of time it exists for, so to speak. And once 5 requests have that timer overlapping, you can't make more at that point. Well, 6 here. But now I can't do more because the spot's already taken. But as soon as it's been 24 hours since that first request, then I'm allowed one more, then another, once it's been 24 hours per request. So that's a sliding window. The benefit of this is that it smooths the distribution a bunch and it's well suited for high load, but it's also harder for a user to understand and predict, and storing the timestamps for each request is obnoxious to do. Totally agree. Yeah, if you do rate limit, send a retry after header. Very much agree. You can see what that is with the MS or the MDN web docs, where you can have a 503 or a 429, which tells you as the user hitting the service that you've sent too many requests and to wait till you make a new one. And there's even a retry after header that you can send that can either be a date or a delay time for how long you should wait until you try again. Back to sliding windows. Because sliding windows tend to be most useful in high traffic scenarios, the fact that the naive algorithm is resource intensive is counterproductive. Shouldn't a high traffic rate limiter use an efficient algorithm? For this reason, most real world sliding window rate limiters, like those provided by Upstash and Cloudflare, they all use an approximation, often called a floating window. Using this approximation, we have all the same benefits, but we can remove the resource intensive point from the cons. Here's how that works. Yes, Upstash mentioned they do these things well. You can count the number of allowed requests in the previous fixed window. You can count the number of allowed requests in the current fixed window. You can weight the previous window's allowed requests proportional to that window's overlap with a floating window ending at the current time. And then you can add the weights from 3 to the unweighted results from 2. So if we see how that works here, we have this imaginary window that exists that knows when requests did or didn't happen. And it can use the average between that window that's just last 24 hours and the window that we're in right now in order to make things a little more reasonable to understand and to give users a rough guarantee of when they'll finally be allowed to do things again without having to store all the same data. In practice, this approach limits requests at roughly the same proportion, but it's far more efficient than tracking all of the requests' timestamps. While the two algorithms will end up blocking different requests, the long-term average number of blocked requests should be very close. You can see below how it compares. I'm going to pause and do the hits all myself. Yeah, it's literally just taking how many hits exist in these two sections and just averaging them based on how much you're in any given one section. So if we were to spam a whole bunch at the end of one of these here, like that, it's going to weight heavily on that left side because they're all near the end. But if I spam them all at the beginning, I should be good to go pretty soon. But I won't be because there's just so many messages that are backed up there. And it is counting the ones that are outside of that little box because it's just averaging the amount of messages in the two boxes and using the split of how much each box is currently in view. It's hard to describe, but it is actually a really good visualizer for it. If I spam this one, so we have all these messages at the start there, I'm not going to be allowed to send more messages right when we get into this new box because even though we only have the second half of that box in there, it is still averaging using the values from the whole box. So that's the key here, is how recently or not recently it happened. Doesn't matter. It just matters which window it happened in. This is a really good algorithm for this. And apparently this is how Cloudflare's rate limiter works. They use an approximated sliding window. Good stuff. Token buckets. People in chat were already bringing this up. Let's see what we have to learn about tokens. Instead of thinking in terms of windows with durations, picture a bucket that fills up with tokens at a constant rate. Each request withdraws one token from this bucket, and when the bucket is empty, the next request will be blocked. The token bucket approach has some useful properties. The first is that the capacity of the bucket is the maximum number of requests that a burst can possibly support, not counting tokens being replenished mid-burst. The other point is that the refill interval represents the long-term average of allowed request interval. Having distinct bursts and average capacities without the need for multiple rate limiters is one of the main benefits to the algorithm. So here we see, it's actually a really nice visualizer. I'll pause so we can do the request manually. This is the request, and we get a new one added to our bucket every, in this case, we have 6 requests, 24 hours. So every 4 hours, that sounds right. Math is easy. So every 4 hours, we'll get a new request in the bucket up to 6. Now I fired one, and we just happened to be near that 4-hour mark there. Now we'll see every 4 hours, we get another request added to the bucket. But if we run out, we can't do any until we get one more of those. But the interesting thing here is we get one more request, and then we can't send any for a bit. Then we get one more, then we can't send any for a bit. Good stuff. The pros of this are that you're allowed to do burst traffic really well too, while still having a long-term average. It's also more flexible, which allows for traffic spikes within acceptable ranges. That's also really nice here, because if I can do a higher maximum because I don't have to worry about the doubling problem, because you can't brute force 12 requests here the way you can in any of the others, especially the traditional fixed window. It's really easy to do things in a way where you have 12 requests really tightly coupled. So if I go back to the top example up here with the fixed window, I'm going to spam a whole bunch near the end, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. Within a very small window, I just snuck in 12 requests. If we have the fixed window with a user-defined start, I can do one request, wait till near the end, and then now when we're getting to the end, I can spam that last 5 and then do another 6. That lets you get 11 in that really tight window. So you can get effectively 2x what you set your rate limit to with these options. With sliding window, it's a little bit harder, but you can still kind of do it. But then with the tokenized version, you can't. The user can't send more than 7 requests relatively quickly. And that only happens if they're near that renewal. So 1, 2, 3, 4, 5, 6, 7. Yeah, cool. And that's it. Now I have to wait another 4 hours till I can do another. So it makes it much easier to define, like within this window, there is a maximum number of requests that can happen. But the big con is it's really hard to explain this to users. So you can't just be like, you can make requests again at this time, because they can, but probably one request. So how do you communicate them when more of these tokens get fulfilled? It's a tough challenge. Apparently, this is how Stripe does things. Stripe uses a token bucket in which each user gets bucketed with limit 500 and a refill interval of every 0.01 seconds. So you're allowed to do a sustained activity of 100 requests per second, but a burst of up to 500 requests. Really good to know. OpenAI's free tier for GPT 3.5 is limited to 200 requests a day, but it uses a token bucket with limit 200, and it refills on 86,400 seconds divided by 200. So you get a full bucket every day, but more importantly, math is hard, you get a new token every 432 seconds, which is every 7.5 minutes, roughly. The Twitch chat demo above is rate limited using a token bucket with a bucket size of 3, allowing bursts of up to 3 requests, and a refill interval of 4 seconds, which creates a long-term average allowed rate limit of 1 message every 4 seconds. For what it's worth, Twitch's slow mode is just doing a fixed window starting when the user sends. So I send a message. Now I'm not allowed to send another message for however long that is. And that's per user because we already store timestamps, so we don't care. Thanks to the flexibility of the token system, token buckets can also mimic the properties of some of the other algorithms. For example, if you set the refill rate to be equal to the limit, and now you have an equivalent to a fixed window rate limiter with a user-defined start. Yep. I don't think I can turn off the automatic here. Oh, it's just constantly going. Yeah. So if you refill the bucket every 24 hours, after a request has been made, you effectively have a fixed window again. Good stuff. Didn't think about this as like a way to re-implement all the other solutions. Kind of like how in React, all of the hooks are for the most part just built on top of use reducer. Like useState is just a use reducer under the hood. Fun fact. Other considerations. If you decide to add rate limiting to your app or endpoint, in addition to selecting an appropriate algorithm, there's a few other things that you should keep in mind, like creating a persisted store for that rate limiter. Yep. If you're trying to scale a rate limiter across multiple servers providing the same thing, you need a place to actually store the information. If you ever intended to horizontally scale your server, or even just restart it or use serverless, also an important point, if you're serverless, you can't just have this be a variable, you need to store it somewhere. Your rate limiter data can't be in memory. A popular option is to save rate limiting data to a key value store, like Redis, which has built-in functions for expiring keys on a separate machine from your application. You can, however, use an ephemeral in-memory cache to block requests without hitting Redis while the limiter is hot. Yep. And this is already what's being used by something like the Upstash rate limiter SDK. So just use that, and this is handled for you. But good to know, you need to make sure this data is stored somewhere. So if the server goes down for a second and comes back up, it has the context. Also, fail open. If your server's connection to the persisted store fails, make sure to allow all requests rather than blocking access to your service altogether. Also important, if the Redis service goes down, you shouldn't block all requests. Ideally, you're letting everything through temporarily. DDoSing your Redis is way less bad than DDoSing your actual database, like exponentially so. Also, optionally throttle bursts. Throttling can be used in combination with rate limiting to reduce the impact of burst traffic. Very good piece of advice. If you can throttle things and that solves your problem, probably worth doing that. Then you don't have to fail requests. Also, choose sensible keys. In general, rate limiting is done on a per user level. For most apps, this means keying on the user ID. For APIs, the key could be the API key. What they mean by key here is how you identify what user is being rate limited or what process is being rate limited. Because if I have like a rate limit for signing in and a separate one for hitting my API, you need a key to identify which is which, and that needs to be unique to the user. Because I don't want all users rate limited for signups. I want one user or one IP address rate limited. One of the best things to do here is to just use like an IP address. They even mentioned that here. For unauthenticated users, the options aren't great, but a popular method is to use the requester's IP address, or a device fingerprint, or a unique installation ID, or just some type of shared limiter across all those users. You can also surface useful rate limiting errors, which you really should if you can. As we mentioned before, use a 429 HTTP status code when the request is blocked, and include the relevant X rate limit response headers. GitHub has a good example of the header for their fixed window limiter, and OpenAI also has some examples for their token-based limiters. This all means that when you hit something and you do hit the rate limit as a developer consuming one of these APIs, you can look at when it says, okay, start again now, and just delay until then. Wrapping up. If you need a simple rate limiter or predictable window start time, use a fixed window. If you need traffic smoothing for high volumes of requests, consider the approximated sliding window. But if you need to support bursts of traffic while also enforcing a lower average long-term rate limit for requests, use a token bucket. This is great. There's even a fun playground at the bottom here where you can see how all of the different things handle different types of traffic. I love this. This really is like a Sam Who article, but not by Sam. Oh, it even says that here. Pre-read. This post was inspired by the amazing load balancing visualizations that Sam's done for his stuff. Also, a huge thanks to Onsclom for pairing with me on the Canvas visualizations. And also a thank you to Upstash for their docs implementation stuff. This was great. This was awesome. Is the author's name somewhere here so I can shout them out? Or is it just like the company? I wanted to find out who this actually is. Does anybody know who this is or their Twitter? Bone Broth, was this actually you? Shit, I didn't even see you in chat before. My bad, Bone Broth. Is there a Twitter I could shout out for you? Give me a Twitter if you have one that I can shout out. But if not, totally fine. This was great. Thank you so much for this. You don't have Twitter? That's for the better. Do you at least have more blog posts? Need somewhere to point people at. Oh, that's actually hilarious. Email and password auth should be a last resort. Couldn't agree more. Seems like we're going to agree about a lot of things by the looks of this. Yeah, hilariously well-timed. Regardless, take a look at Smudge AI. Fantastic stuff. Love this blog. Really nice to have good information about these things, and honestly kind of surprising there wasn't already a good article like this about rate limiting. Let me know what you think in the comments. Let me know how you're handling rate limiting on your services. Until next time, peace.